Welcome to 3D World with our geometry excursion. Today we're going to be looking at 3D shapes and figuring out volume and surface area on those. And this will wrap up our geometry unit. Lots of formulas in store. Let's take an adventure and figure out how these formulas come about. And hopefully that will help you remember them instead of trying to memorize all of them. And then we'll have a couple of other little experiences in there too, besides volume and surface area. But let's start with volume and surface area. What are they? Well, I'm going to be developing these formulas side by side, so let me just go ahead and tell you what both are. Volume tells you how much space is inside of a 3D figure. So if you need to fill the figure, how much substance can fit. You've already been doing measurements back in the previous chapter, chapter 7. And you had to work with volume, cups, gallons, liters, milliliters. Those are all measurements of volume. So is cubic centimeters. How much does it take to fill up something? So we're going to be looking at those. And when we figure out the volumes of objects, it's going to be in cubic units, like cubic centimeters, cubic inches, things like that. Then not only are we going to look at how much is inside the figure, we're going to look at the exterior too. The surfaces, those faces. Imagine that you were taking an object and trying to wrap it. In my case, holidays are coming up in a few short months, so I'm starting to think about gifts and trying to get some wrapping paper. And let's say I wanted to be super nerdy about it and wrap my presents with exactly the amount of wrapping paper I need. No more, no less. So that means, cutting it and covering so that my gifts have no overlaps, no gaps in the wrapping paper. Well, figuring out how much wrapping paper is needed to do that is a measurement called surface area. The surface area, and that's going to be in square units. It's area. So it's going to be square inches, square feet, square miles, and those kinds of units. Okay, so let's start with the rectangular solid. Rectangular solid, think about rectangular solid as being a box. Has rectangles for faces. These flat parts on here are called faces. Where the faces meet, these little line segments are called edges. The little corners where the line segments or edges meet are called vertices. Well, rectangular solid, the faces are all rectangles. So let's first develop the formula for the volume, and then we'll develop the formula for the surface area. Okay, so volume first. Just like, how area, you were trying to figure out, well, how many little squares fit inside of a figure. So then you got square units for area, right? Well, for volume, when you have something like a box, you're trying to figure out how many little 1 by 1 by 1 cubes will fit in that figure. So be patient with me while I sketch something out that has cubes in it. Okay, so in the case of a box, you're trying to figure out, well, how many of these little 1 by 1 by 1 cubes would fill up that box? Well, first of all, to see how many cubes are just in one layer, Notice you've got 1, 2, 3, 4, 5 across this way, and you've got 1, 2 going back that way. So one layer is 5 by 2. So you have 5 times 2, or 10 cubes. So that one layer has 10 cubic units. And you got that by multiplying length times width, 5 times 2. And then you've got, what, 1, 2, 3, 4 layers of this? Because the dimension of the height is 4 layers of 10 cubic units each. So 4 times 10 equals 40 cubic units in the entire box. And that's the volume. The volume's literally trying to see how many, if you're doing inches, it's 1 inch by 1 inch by 1 inch. If it's feet, it's 1 foot by 1 foot by 1 foot. If it's centimeters, it's 1 centimeter by 1 centimeter by 1 centimeter. How many of those little blocks, those little cubes, can fit inside your shape? And I went ahead and used nice whole numbers so that we didn't have to worry about parts of blocks. But even with parts of blocks, the process of figuring out how many is the same. You can do your length times width. So taking care, let me draw just another rectangular solid real quickly here. You can do length times width to see how many are in one layer, and then multiply that by height to see how many are in all the layers together. So that's the volume of the box. Length times width times height. That's how it's done. So it's the three-dimensional version of finding area. You have to add that third dimension of height in there. Okay. So that's for volume. Now when it comes to surface area, think about your box again, and this time think about wrapping it using wrapping paper. For a box, the faces are all rectangles. Okay, so you've got your length, your width, your height. Okay, so let's say you want to find the area of the top. Like just figure out how much wrapping paper do I need just to fit on this top exactly. Well, the top is length by width. Length times width, 'cause it's just a rectangle. And the area of the bottom is going to be the same thing. Because top and bottom are identical. Okay, area of the front is length by height. But you know the area of the back is the same because the front and back are identical. Also length times height. Area of the right side is going to be width times height. And so is the area of the left side. So your surface area has to be your top plus your bottom plus your front plus your back plus your right side plus your left side. And if you want to clean that up a little bit, you have 2 of these LWs plus you have 2 of these LHs plus you have 2 of those WHs. There's your surface area formula. So if you want to see just how many square inches or square feet of wrapping paper you need for a box, you can do twice the length times width, plus twice the length times height, plus twice the width times height. Now be careful though, because measuring it out and getting the right shapes, you might have to take your box and trace it onto the wrapping paper and cut those out. But at least you're able to figure out, well, I need at least this much wrapping paper to do it. Alright, and there's the formulas again. For a rectangular solid, you got your volume and your surface area. You're going to have problems where you're going to have to find volume and surface area given those dimensions. So remember, volume's in cubic units, surface area is in square units. Alright, now I made mention of a cube already. I'm just kind of assuming you guys have that prior knowledge of what a cube is. But a cube is a rectangular solid. It's a box. All the faces are squares. So it's a box where you have all the same square making up the faces. So not only are they squares, but they're all the same size. So since all the faces are squares, your length, width, and height are all the same. So for volume, you can say length times width times height because it is a box. It is a cube is a type of rectangular solid. But since the length, width, and height are all the same, what you'll often see is that they'll use an S for side, like side length. So then you can summarize volume by saying S cubed. The side length, the edge length. Some books will say E cubed for edge length because those little line segments where the faces meet are called edges. And then for the surface area, it's just like your box earlier, your rectangular solid. Remember how we had surface area equals 2LW plus 2LH plus 2WH? I might have gone in a different order, but it really doesn't matter as long as you've got all three of those represented. But in the case of our box, remember L, W, and H are the same in the cube. So we just replace that with an S for side length. And again, I try to do these fancy little swirlies for S's so that you can tell them apart from my 5s. So you have 2s squared plus 2s squared plus 2s squared, which is really 6s squared. So if you want to find out, well, how much paper is that, how many square inches of paper is that, it's whatever the edge length is, the side length is, squared times 6. And when it's unfolded, you can see it. Unfolded, it's 1, 2, 3, 4, 5, 6 squares. So literally what you're doing is you're finding the area of a square, which is side squared, and then timesing that by 6 of them. So 6 times the side squared, times the area of one of the squares. And all the squares are the same, so you can just multiply by 6. So there's your cube formulas again. Remember, volume is in cubic units, surface area is in square units. Alright, various prisms. Rectangular solids are types of prisms. What is a prism? A prism is a figure where you have your top and bottom are identical polygons, and then the sides are parallelograms of some kind. If the prism stands straight up and down, then the sides are rectangles. So you have an example here. You have a hexagonal prism. This is an example of a hexagonal prism. Hexagonal right prism is standing straight up and down. Some prisms can lean a little bit, kind of like Leaning Tower of Pisa. But this one's it's right if it's standing straight up and down. And this is a right triangular prism. You could have said right hexagonal prism there too. You could put the word right in the front. And if you want to find volume of a prism, it's the same thinking as your box. It's the same thinking as your box. Area of the base tells how many cubes make one layer. Height gives the number of layers. So if we have number of cubes in one layer times number of layers, that'll give us our volume. So what we do is you write capital B, and that stands for area of the base, times H, which is the prism height. And that'll tell us the volume of any prism. If you can find the area of the base, whether it's a triangle, a hexagon, a trapezoid, a rectangle, whatever it is, find the area of that base, multiply by your height, and you'll have the cubic units for volume of that figure, of that prism. So capital B stands for area of the base, while lowercase b is typically a length, like in a triangle, the length of the bottom of the triangle. So capital B stands for the whole area of whatever the base is for that three-dimensional figure. Alright, pyramid. So let's break out of prisms and go on to pyramids. It almost sounds like a TV show, break out of the prisms. Prism break. Alright, going to pyramids. If you start staring at pyramids, you start to see that they have some similarities to prisms, but instead of having the same polygon on the top and bottom, what they do is they have a polygon on the bottom, and then they have these triangles that come up and meet in a point. Make a vertex there at the top of the pyramid. So the prisms had rectangles for the sides, or parallelograms if the prism's leaning. Whereas a pyramid, you're going to have triangles for those sides. But there is a relationship between a pyramid and a prism that have exactly the same base and the same height. When I say height, I mean straight up, like from this little tippy point here, straight down to the ground. Not the slant height along the triangles. And the way they're related, we have to think about, well, how many of these pyramids would fit into one of these prisms? If you had the same exact base, same straight up and down height, how many pyramids would it take to fill the prism? Well, let's do a little experiment with some rice. I did the experiment, took some pictures. Let's see what happens. I took that pyramid and I filled it to the top with rice, and then I dumped it into my prism. Already you can see, well, it's not just one. It's going to need more than one pyramid to fill the prism. But in your mind, take a guess about how many you think it's going to be. 2, 3, 4, 2.5. I'll give you a hint that it is a whole number. It's not in fractions. Okay, there's my second pyramid of rice dumped into the prism. So it's more than 2. And there's my third pyramid dumped into the prism. It took 3, not 1, not 2, but 3 pyramids to fill my prism. So what can I say then about the pyramid's volume related to the prism's volume? Well, if it takes 3 pyramids to fill the prism, then that means the pyramid is 1/3 of the volume of the prism. So the formula then is a snap. All you got to do is use the formula for prism, which was area of base times height, and do 1/3 of that, and you've got your pyramid. It's 1/3 times the area of the base of the pyramid times the straight up and down height of the pyramid. So there's your volume. The surface area of a pyramid is a little more exciting. You're not responsible for it for the test or really for any homework, but I just liked the little picture I made, cutout I made when I did this. The pyramid's base, in this case, the pyramid's base is a square, but the sides here are all triangles. So if you want to find the surface area, you got to find the area of the base plus the areas of those triangles. And all 4 triangles are the same, so just find the area of one, and then times that by 4. You've got the 4 triangles. Add that to the base. There's the surface area. I don't know why we don't require you guys to do that one, because I think it's rather fun, but we don't, so don't worry about it. Oh, and by the way, too, if you're trying to find the area of the triangle, you're actually using what's called the slant height of the pyramid. It's that height of the triangle itself. Whereas earlier when we were doing volume, we were using the height from the top point straight down to the ground. It's like a tent pole in the middle, the height is for the volume. Alright, let's progress from prisms and go to cylinder. The only kind of cylinder you guys have to worry about is a right circular cylinder, like we have here. So we will focus on right circular cylinder. Right means it's standing straight up and down, so thank goodness you don't have to worry about anything leaning. And cylinders don't have to have circles, but that's what you're going to have. You're just going to have circles to worry about. You can have ellipses and stuff for your cylinders. So you can have other top and bottom shapes, not just circles. Alright, cylinder. Finding the volume is just like finding the volume of a prism, honestly. Area of the base times the height. But in this case, the base is a circle. And the circle's area is what, kids? Pi r squared. Woo. Okay, so when you go to find the volume, you're doing pi r squared h. So on your cylinder, little can, the r is the radius of the circle, and then the height is the height of the can or cylinder, the cylinder, how tall it is. You're using those dimensions along with pi and finding the volume that way. Because literally, what you're doing here still is you're seeing, well, how many little cubes would fit on the first layer, and that's what pi r squared, or the area of the circle, tells you. And then the height tells you how many layers of cubes you could put in there. So you're timesing the number of cubes in the first layer times how many layers there are to see how many little cubes fit. Now surface area, you are going to have to know how to do surface area of a cylinder. Not so bad. Notice in my picture over here, top and bottom are circles. So the areas for those, you're going to need 2 times pi r squared. But for the soup label part, I don't have a technical name for it, it ends up being a rectangle when you unfold it. So you're going to have to use, length times width, but you're going to have to be a little creative in how you figure out length times width. Because remember, this is a cylinder where you're going to be told radius of the circle and then this height. That's what you're going to be told. So you got to think about, well, how does length width translate here into this soup label? Well, the soup label, when you unroll it, you You can see this part here is the same as the height of the can. This dimension, though, is a little trickier. But notice that as you unroll the soup label, the soup label fits perfectly around this circle. What is the distance around the circle? That's the circumference. Let's go ahead and use 2 pi r, since we have things in terms of r. So this dimension of the rectangle is actually the same as the circumference of this circle. Because when you unroll that rectangle, when you roll it up, it fits neatly around the can. So LW equals 2 pi r times h. So you add them all together, and the surface area of your can is going to be the 2 pi r squared for the top and bottom, plus the 2 pi rh for this soup label, the rectangular soup label. And that's your surface area of a cylinder. And there's your formulas again. Volume is pi r squared times height. Surface area is 2 pi rh plus 2 pi r squared. Alright, cone. The cone's related to your cylinder in that the base can be the same as a cylinder. And the height from the tippy point here straight down, that's the same as the height of a corresponding cylinder. And if you think back to our little demonstration with pyramid and rectangular solid, the cone and the cylinder have the same relationship. When you're asked how many of these cones will fit into one of these cylinders, given the same base, same height, I did the experiment with rice and had 1, 2, 3. It fit 3 of them fit into that cylinder. So the volume of the cone is 1/3 that of the cylinder. Remember, the cylinder is pi r squared h, so the cone is 1/3 pi r squared h. So there you have it. So the cone volume is 1/3 times pi r squared h. Surface area gets a little complicated. You do not have to know how to do it, but I just liked having the little cutout. I thought it was pretty looking. The circle's easy. You find the area of the circle. This part's not so easy. It's a fraction of a circle, but it's not a nice simple fraction. We're not even going to worry about it. If you want to look it up and see what the formulas look like for these ones that we're skipping, there is a chart on page 470 in your book that has volume and surface area for the 5 shapes there. Sphere, a ball. Finding the formulas for a sphere at first look kind of random, but there's actually a relationship between a sphere and a cylinder. Let me draw this out for you. Oops, sorry, I was trying to get my ink color. Let me change my color for a second and draw a cylinder. Actually, let me draw the sphere. And then let me use a different color. I'll go back to black to draw the cylinder. If you take a sphere and fit it perfectly with a cylinder, if I can do this justice with my drawing. Oh, don't do that. Okay, let's say you fit a sphere perfectly into a cylinder like this, where like this big great circle of the sphere is also a circle around in the cylinder there, in the can. Both the volume and the surface area of a sphere are 2/3 that of a cylinder with same radius and height equaling diameter. So in other words, like the height of the cylinder is the same as the diameter of the sphere. Okay, so if we're talking about volume of the cylinder, we have pi r squared h. Well, the volume of the sphere should be 2/3 of that pi r squared h. Thing is, though, the sphere we don't really talk about in terms of h. The h here, h, is the same thing as twice the radius, because you got radius up, radius down makes your height. So you can replace h with 2r. 2/3 times 2 is 4/3. R squared times r is r cubed. So the volume of the sphere is 4/3 pi r cubed. But that comes from 2/3 of pi r squared h. It's just h is 2r, twice the radius. Okay, and then for surface area of the cylinder is 2 pi r squared plus 2 pi rh, right? The surface area of the sphere is going to be 2/3 of that. Okay, before I go too far though, remember h is the same as 2r. I just looked at that a minute ago when doing volume. So replace the h with 2r. So in parentheses here we have 2 pi r squared plus 4 pi r squared, which comes out to 6 pi r squared. If you do 2/3 of that, 2/3 times 6 is 4 pi r squared. So the surface area of a sphere, take the radius, like it's like pi r squared, like the area of a circle, times 4. But that comes from the surface area of the sphere being 2/3 that of the surface area of the cylinder. So if you can remember that, if you know the cylinder formulas, do 2/3 of those and you'll have the sphere formulas. And just remember h can be substituted with twice the radius on a sphere. But there you go. There you have it. There's the sphere formulas again. So once you know the radius, just plug it into these formulas and you got it. Some folks on the test will get confused and say like volume is 4/3 pi r squared and that surface area is 4 pi r cubed. Remember, volume is in cubic units, and here you have r cubed. Surface area is in square units, here you have r squared. So just kind of remember that too. And volume has the 4/3. You got a 3 here, a 3 there. Remember those are together in the same formula. Surface area, it's like you're cutting up 4 circles and pasting them onto your sphere to get the surface area. Alright, let's talk about cubic units. Just like in the last lesson how you had square unit conversions, well, you've also got cubic unit conversions. Remember, 3 feet equals 1 yard. So 3 squared, or 9 square feet, equals 1 square yard, because 1 squared is 1. 3 cubed is 27 cubic feet, and that equals 1 cubed, or 1 cubic yard. So you got 27 cubic feet equals 1 cubic yard. Remember, 100 centimeters equals 1 meter. You square that, you get 10,000 square centimeters equals 1 square meter. Or if you cube that, $100 cubed, you got 1, 2, 3, 4, 5, 6. So you got 1 million cubic centimeters equals 1 cubed, or 1 cubic meter. So be able to do some conversions with those. Throw that in here too, just like working with these cubic units, this volume and stuff. So if you have something like 6 cubic yards equals how many cubic feet? Well, there's 27 cubic feet per 1 cubic yard. So we got to figure out how many cubic feet go with 6 cubic yards. So you have 27 times 6 equals 1 times x. X equals 12, 162 cubic feet. Or you might be going 500,000 cubic centimeters equals how many cubic meters? Oh, we said what, 1 million cubic centimeters in 1 cubic meter? That was the conversion factor. And you're trying to convert 500,000 cubic centimeters into cubic meters. So 1 million times x equals 500,000 times 1. So 500,000 divided by 1 million. Cross out 5 with zeros, you get 5/10. Something 0.5 cubic meters. So make sure you know how to do those conversions. Let's see. Let me do one more thing. Let me insert a slide here. It might not let me do it right now. I'll save it till later. Let me go over Euler's formula, and then I'll do an example of one of the homework problems. There's some homework problems where you have to find volumes of shaded regions. I definitely want to do one of those before I sign off, but let me go over Euler's formula first. Euler's formula expresses the relationship between the number of vertices, edges, and faces in a polyhedron. But before seeing the formula, let's define a few terms. A polyhedron is a figure made when polygonal regions are joined to make a closed surface. So all of our prisms and things and pyramids we were looking at earlier, those are all polyhedra. Each polygon is a face, each line segment is an edge, each point is a vertex. A polyhedron that has all faces that are the same size and shape is called a platonic solid, or a regular polyhedron. So like a cube is a regular polyhedron. All the faces are the same size square. And then a prism is a polyhedron where you have congruent polygonal bases. So top and bottom are the same, are congruent polygons, like two triangles or 2 squares or 2 hexagons or whatever. They have to be congruent. And then parallelogram sides. If the prism stands straight up and down as a right prism, then the sides are going to be rectangles. Alright, I just want to take a look real quick in your book here. Yes, I'm going to keep the annotations for you guys. I'm going to switch over to your book real quickly, because normally I would do this on the dot camera in class. But pages 473 and 474 have some nice little drawings, way better than I could ever do. And I tried to pull out my son's little magnets and build some of these shapes, but it just got a little out of hand, so I figured I'll just show you guys what the book has. It has some pictures of some polyhedra here. Closed surface made by the union of polygonal regions. So here you've got polygons joined together, make a nice closed shape. Little points, the little corners are vertices. Each one's called a vertex. The little line segments are edges. And then the polygons themselves are faces. So you can have it. You can have pyramids, and you can have other kinds of shapes too that are polyhedra. Then it talks about platonic solids, regular polyhedra. There's only 5 in existence. These were what I was trying to build with my son's magnets. I could build the tetrahedron with no problems. It's got 4 faces. It's 3 congruent triangles, or 4 congruent triangles, sorry. You can see 3 in the picture, and then there's one hiding behind in the back. 4 vertices, 1, 2, 3, 4. 6 edges. You got 1, 2, 3, 4, 5, plus the extra. Hang on, I'm missing something. 1, 2, 3, 4, 5, 6. You can see all 6. Cube has all squares for faces. 6 faces, 6 squares. 8 little corners, vertices, and 12 edges, 12 segments. Octahedrons, kind of like the tetrahedron with triangles, except they've managed to fit together 8 of them. Icosahedron has the triangles again, but they've managed to fit 20 of them together. And then a dodecahedron has regular pentagons put together. Sort of kind of reminds me of a soccer ball, but soccer balls are what, pentagons and hexagons? Makes it a lot rounder. But these are the only 5 platonic solids possible. These are the only 5 regular polyhedra you can have. I thought that was interesting to look at. And then the next page, they show you some pictures of prisms. Remember, a prism, top and bottom, are polygons that are the same, but are congruent. In a right prism, the sides are rectangles. So you have a right triangular prism here. You have, looks like a cube here. If nothing else, it's a right rectangular prism. You have a right hexagonal prism here, and a right trapezoidal prism here. Top and bottom are congruent trapezoids. Sides are rectangles. But there you go. There's some pictures of some of those shapes that we were just talking about in the in these definitions. Okay, so let's go back now and let's look at that Euler's formula, which you probably already saw a glimpse of it when we were playing around there on those pages. But for these polyhedra, Euler figured out that there's a relationship between vertices, edges, and faces. Turns out if you take the number of vertices minus the number of edges plus the number of faces in a polyhedron, it's always going to be 2. Okay, let's take this right rectangular solid, for example. Let's do that. This box has 1, 2, 3, 4, 5, 6, 7, 8 vertices. 8 of those little sharp corners. This box has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. And faces, you got top and bottom, front and back, left side, right side. So you get 6 faces. Well, 8 minus 12 is -4, plus 6 is 2. It's always going to come out to 2 for your polyhedron. Alright, we got a hexagonal prism right here. Vertices, there's 1, 2, 3, 4, 5, 6 up top, and then it repeats with 6 on the bottom. So you have 12 minus edges, where you have 6 edges for this hexagon, 6 edges for the hexagon on the bottom, and then 6 edges for for the rectangles on the sides. So that's 18. Plus faces, you got top and bottoms 2, and 1, 2, 3, 4, 5, 6 of these rectangles. So that's 8. 12 minus 18 is negative 6, plus 8 is 2. And down here's the square pyramid. Vertices, you got the 1, 2, 3, 4 for the square, plus this one top point, that's 5. Edges, you got 1, 2, 3, 4 sides of the square, plus 1, 2, 3, 4 sides of the triangles, so that's 8. Plus faces, you have the 1 square and the 4 triangles is 5. 5 minus 8 is negative 3, plus 5 is 2. It's always going to come out to 2. Pretty remarkable, really. Pretty amazing. It always comes out to 2. VEF. I remember VEF. It's V minus E plus F equals 2. Alright, as I promised, I just inserted a slide, and I'm going to go ahead and do an example problem from a book with you guys. You're going to have a 3D version of something that was in the last lesson where you had to find the area of the shaded region. Well, now you have to find the volume of the shaded region. Okay, and I'm actually going to pull number 25 out of the textbook, where it gives a box Yeah, I don't want that line there. I'm trying to draw a box. Goodness gracious, why does it do this to me? Okay. Okay, we have this box, and I'm told that it's 3 feet by 3 feet by 4 feet. So apparently the bottom's a square. The base is a square, the height is 4 feet. It's rectangular solid. Then inside of this rectangular solid is a pyramid. Whose height is the same as the height of the box. The shaded region is all this space outside of the pyramid. So we got to find the volume of the box, which is length times width times height. So 3 times 3 times 4 gives us 36 cubic feet. And then since the pyramid has the same height as the box and has the same base as the box, it's going to be 1/3 the volume of the box. So that's 1/3 times 36, or 12 cubic feet. And then the volume of the shaded is the box minus that pyramid. So 36 minus 12, which gives us 24 cubic feet. Or the shaded is 2/3 out of the box. So remember the pyramid was 1/3 of the box. So 2/3 times 36 will get you the same answer, 24 cubic feet. So these problems, you're going to be finding volumes of a couple of shapes, and often either So often you'll subtract to get the difference and see what's left over for shaded region, but other times you're going to add. It's just depending on the shape, on what the figure is. So just look very carefully at them. Make sure you practice those, because you'll definitely see those again on your test and possibly on your final exam. So practice, practice. All right, and as you saw from the flub a second ago, that is it for this lesson and this unit. We're not going to do any more of this chapter for this course, and in fact, we're going to skip several chapters. And when you tune in again for the next unit, we're going to be in chapter, way down in chapter 11, which is all about probability. So that's it for geometry. Make sure you practice, learn the formulas, but piece of advice, learn how to get the formulas. Don't just try to memorize them. Makes it so much easier. And I look forward to tuning in with you again soon.